have some like pools running while people is presenting, and the idea is to have like an anonymous vote, so to say, whether you, in three questions, because it was a free version, I don't want to pay for more. So we have the broader problem, the narrow problem, and the take-home message, okay? So the idea will be for the person who is presenting here to get like your opinion, if you have gotten or not the broader problem, the narrow problem, and the key, and the take-home message. And you also will have this answer. This is important too, because the idea is to give to the person like a real feedback. It's a very naive feedback, but still. So if you did not get the broader problem, you also have this option. I was not paying attention, and this is fair enough. And it also helped the presenter, because at the end it's good for them to know whether they capture the attention of the audience. So let's try to be very like honest on the pool, okay? And for the people that will come here to present to present and to try to practice these presentations skills, then you have to take this as a very constructive feedback, and you can just improve, and you are brave enough to come here and to try it, okay? So don't take it like personal or something like that. So we will start with the presentation of Leticia. So come, Leticia. Where is it? Where's the... I don't know where the bus. Aquí, here. Huh? Ah, yes, it's better. No, it's better if you use them. Is the micro? Since we don't have the 30 presentations as I wanted to, we can have like 3 minutes plus 1, okay? So let me see if I can put the chronometer.
I don't know which side is better.
Okay, let me know when you're ready.
Yeah. Okay, let's go. I'm going to put here also. Well, thank you very much. Good morning, everyone. I'm Leticia, and I work in Concepcion in Chile. Okay. Oh my God, my time.
Will not follow you, and the important thing.
Stop the.
Yes. Now we know. Everyone has to put this thing. Okay. Now we restart the time.
Yeah. Okay. It's fine. Oh, so nice difference. So, how was I saying? I'm Leticia. I work in Concepcion in Chile. In the group of Professor Steve. And actually, my work that I'm going to present here is about Hongamando interference and using the multi-core fibers that Professor Steve already said a little bit in the classes before. And then I'm going to use this effect to do a task. It's a measurement task to see how we can use this effect to do some precision measurement. And which scale we can achieve with this effect. So at the first slide, I already put some of the Hongamando effects, and just I'm not going to show everything here because Steve and the other Professor Daniel also make the mathematical things in this case. But just a reminder, the Hongamando effect is the two-photon interference. So when you have two photons enter in a beam splitter, and then you can characterize each one of the inputs like a mode. You have two modes in the outputs also. You can define the annihilation operators for this effect of the beam splitter. And then you have 4 possibilities. So half of the time, if the photons are interacting and are indistinguishable, they will interact and go out together in one output, or the other one, or they, half of the time, can go out separate ways when you have distinguishable photons. So if you put a detector in the outputs and analyze the effect of the BS in this input state, I don't see. You have this output state here when you have the interference and you have 2 photons in one mode or 2 photons in one. So you have an output state like a superposition this way. And this is important also for like engineering, entangled states and better state analysis and something like that. This is a typical experiment of HongoMondo. And so for example, you have a laser source, you send for a crystal, and then for a process of conversion, spontaneous, I don't know exactly is this SPDC or not, but you generate a pair of photons, and then you send in separate ways these photons, and then you make them interfere here and then detect. And then the thing is, you can change one delay of this arm of the interferometer, and then in this case, they were taking a measurement of the time shift. So if you change the displacement of this arm here, you can like map the coincidence counts of this displacement. And then an experimental signature is the home dip, because this effect of this dip, it means that the times that you have the coincidence counts is this case here. So you have like a number of coincidence counts, but when you have the interference, this coincidence goes to 0, theoretically. So when you see this in experiment, is that it's a way to see some invisible. So we are seeing the interference of the photons. And that's it. And so the idea was to extend this to a model of this kind of interference for a 4x4 BS. Because there in Concepcion we have these multi-core fibers, and then we can use this as a beam splitter using these 4 cores. So you can characterize the matrix of this beam splitter like this. And then you do the same, basically the same mathematical description here. You have the output state. So due to this bosonic symmetry of the photons, this interference of indistinguishable photons lead to non-classical correlations. In special, the bunching and anti-bunching effects. So the interesting thing here is that in the 2x2 BA splitter, you can see only the bunching effect. But if you have 4x4, you also expect to see the anti-bunching effect. Will be the peaks and not only the dips if you analyze the probabilities of coincidence. Yeah. So this is an experiment. I'm not going to talk in details about this. If you want to see more, you can go to the poster later. But in short, I have this part of above of the experiment. I have the source on pair, so the source of photon pairs. It's entangled in polarization. And then I send this to an interferometer. But our interferometer, as I said, is composed by the multi-core fibers. And then we send to the SNSPD, because it's superconductor nanowire detector. It's very good. And then we detect the outputs and make these plots. So this is like a result of one measurement. So as we expected, we see the dips of the sum of combinations that we have, the interference, the destructive interference, and you see also the constructive interference of the anti-bunching effect. And you can, from this graph, you can take some information, like for example, the visibility. The visibility gives you how distinguishable are the photons between them, and also the coherence length is given by this FWHN. It gives like the how much time your photons are interfering. So the idea of the task is to make a measurement, like I say, in a sub-picosecond precision. Is the original paper of the HongoMondo. It's intended to do something like that, to make a measurement in this scale. And so the idea was, we have the 4 cores of the multi-core fiber, but each one of the cores has a slightly difference in the refractive indexes because of some fabrication difference or something like that. So if you are sending you're sending photon pairs, I don't know, you want to do some communication protocol, something like that, it's important to synchronize your pulses. So if you have a huge dispersion between these modes, it can be a problem. So to solve this, we can use this effect to characterize how much is the dispersion between these cores of the fiber. So this graph here are several Hongo bundles that we made for the different combinations of inputs of the fiber. And then we took the difference between these dips, or the peaks. And then we see how this dispersion increases with the length of the fiber. Because in theory, this tends to accumulate with the length. So we made this for several fibers. And then this graph, it's only 3 points, but I swear that I want to have more points until the publication. And then the idea was to see how this mode dispersion increases with the length of the fiber. And then each one of these different colors is for a difference between the input delays and this opposite. Because if you connect them in 2 inputs and make a Hongo bundle, and then we turn in the opposite way and do the Hongo bundle, you see this displacement between the dips. And this is the difference between the intercore delays that I want to characterize. And then the number that I took from this experiment was like 21 picoseconds. And that was like an example to see how it works, how you use the Hongo bundle to do a measurement text. And that's it. Oh, sorry.
This is normal when you are trying to do this little flash talk, so you have almost 3 times the timing. So it is hard. So since we don't have many people register, we can also try to just like you keep going, and then we see how much of
I have a reversal. 4 minutes.
No, but it's normal. When you are here in front, you have like 2 things that can happen to you: that you either talk too fast, and then you are like below the timing, or you explain more things, and then you are above the time.
Case, yeah.
This was the case now. Okay, so we will.
Thank you very much.
Do you have questions?
Questions?
Do you have questions, since that we don't have
question.
the 30, we have, let me see how many. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 16, so we have a bit of time for questions if someone wants to ask, and then we do the pooling.
Questions? Yeah. Yeah.
Repeat the question for everyone, and then answer.
Here's asking me about the last figure, about the difference time in the fibers. The last one, yeah. Because I passed through the explanation. But when you have the Hongo bundle dip with 1 input state, you have 1 dip, and then I change the inputs. I just switch them, and then I took another. But I have 4 cores, so I have 12 combinations. So to see how this EGD that I call the difference in delay will increase with the time, you took a root mean square of these values. So each one of these colors are like one of these switch for the 1 combination. And then I made all the root mean square of all these combinations. And this, it will increase with the length, on the theory, yeah. Because this goes, actually, I'm characterizing this now, but in the literature, there's a thing called polarization mode dispersion. Then if you have a medium and you send a pulse, you have the polarization in vertical and the other one. And then if you have a difference in the refractive indexes of the axis, at the end of the median, you have this delay in the polarization. So originally, the idea came from here, from this thing. So the idea was to make an analogy with this, but considering each one of the cores of the fiber 1 mode. So it's not a polarization mode dispersion, but it's like an intercore mode dispersion. And then we are seeing if this follows also this random walk relation that goes with the...
Then you can keep discussing in the coffee break. So we will do the pool now. So the pool for the Broden problem starts now. So you can make your votes. Sí, porque se la vamos a pasar al siguiente. Sí. If someone wants to volunteer for the next, you can come and take this. Otherwise, I will just choose. But okay, thank you. Okay, so we stop this one. So no one can vote any longer. Okay, so this is the result. So you see, for a lot of people was still not clear. For others they were not paying attention. I don't know how to say exactly the numbers of the votes here, but it's something like that, Leticia. Okay. So let's go for the narrow problem. Now you can vote. I will try to make it in 30 seconds, okay, this, in order to not lose more time. Okay, we stop. So this is for the narrow. So here you see, like this is normally it's very usual that people when you are a student, especially you can explain way better the narrow problem than the broaden problem, and people can follow you easily on that. So this is a very normal situation. So we will go now with the take-home message, with the main thing that she was explaining to us. Okay, we stop. And then, again, the same, because you know way better about what you are actually doing, and then people can follow you easily. So it's the very by book results, okay? So now we will start with the second presentation. So which one is yours? Felipe, pero ¿dónde está? Aquí está, que ya la vi. Okay, then let's do this. No, this is view. Enter full screen. Okay, now you can go.
Hi to everyone, my name is Felipe Quinteros from Universidad de Concepción, as well as Leticia. Well, I work in non-Markovian regime in waveguide QED. I will explain a little more all the title. To begin, my work is based on Dick superradiance. He proposed that to have superradiance, we need to have a cloud of atoms that are packed in a distance that is smaller than the length coherent of the emitted photons, okay? But today, the community are moving from cavity QED to waveguide QED, so we can explore another type of regimes. For example, when we have two atoms that are at a distance that the delay is of the order of the lifetime of the atoms, we can have a real interesting scenario where if the single emitter length is of the order of the distance, they will interfere. So they will make superradiance. And superradiance have a shorter length of the pulse. But then they don't will see each other, and they will send in an independent way. And then it's an interference process, and this will be build up some nice phenomena. So to solve this, we need to solve the equations in a non-Markovian regime. This has been done with Pablo Solano, that is my professor, and Kanu, and Pablo Barberis, and William. And they find that, for example, if they both are really close, you will have like a superradiance. But if you have them really far apart, you will see independent emission, this is the probability of have one atom excited. But these two regimes, they don't see each other, or they are really close and see each other from the first time. And what is interesting, that if you make this non-Markovian regime, you will have this steady-state solution at the end. That is a formation of a dark state, that is 2 atoms that don't emit the photon, plus 2 photons bounding the continuum. That means that they are in a stationary wave between the 2 atoms in the ground state. And this is really cool because this is a way to prepare dark states, because it's not really easy. And this is a truly non-Markovian way to make this. It's because the state in some moment pass through a mixed state, so excited these eigenvalues of the dark state and start to build up. And well, my work is, this calculus has been done with 2 atoms and 2 excitations, starting with the 2 atom excited. But what I do is, what happens if I repeat the process and start adding more photons and more photons and more photons. So at the beginning, we have this dark state plus the VIC state, and I send 2 pulses perpendicular to the waveguide. So the stimulated emission goes outside the waveguide. And the dark state is symmetric under this interaction. And the 2 photon VIC will give us, again, the 2 excited atoms. And this will evolve, again, to some kind of this state. And we will have a 2 type of dark state, one with 3 photons between them, one with 1 photon between them, and finally a 4 photon VIC state. So we can start building up dark state generation, and also maybe photon storage, and maybe deterministic photon release, and maybe. So this was really long work. We find this equation to the dark state generation, and the funny part is that depends a lot of the frequencies of the photons. But since they are in this steady state way, they form this frequency comb Fabry-Perot pattern, and we think that what's the problem is that for some frequencies, this could be lower than the previous result. So maybe don't add dark state generation. Maybe you are starting to lose this state. So we need to figure out how to control the frequencies of the photon that are emitted. And this is my poster. If you have some question, you can ask me. And another work I want to show is the master student work, Franco, that he make another question. What happens if instead of having 2 atoms, I add more atoms? This is not really trivial, but we have a theorem that is the final value theorem that said that you will have some steady state every time some poles are 0. So you can make some numerical analysis to start finding what are these steady states. And he find that for 4 atoms, you will have the one I showed, plus 2 excitations in 2 atoms. And you are going to start building up this dark state that, I don't know if it's called that way, but entanglement between atoms in pairs, okay? And, well, if you have more questions, you can ask me. And this is the group that we are working. It's my professor, Pablo Solano, Pablo Barberis, a professor of Mexico, Franco, this is the master students, me, and also Gabriel that don't send me the photo. Thank you very much.
So this was almost 7 minutes again. So I say this is difficult, so it's okay. Do you have any question for Felipe? Yeah.
So as Carla said, it's very common to pass the time. But for example, this kind of slide in a 3 minutes presentation, it should not be there. And like, this is for everybody. You have 3 minutes. You're losing time to say the other people. So you see, it's a precious time for you. So it should not be there, this slide.
Yeah, no, this is important. The comment, I can also give you feedback to each of you, but it's true. When you have a 3-minute presentation, what I do sometimes that I put the picture of the people in the first slide, and then everyone can read, and that's it. Okay. So let's go to the pool, because we have other people to come to. Let me go here and have to reset the results. Okay, so now we will go to the, yeah. So we go to the broader problem. Gracias, Felipe. Okay, so it's this. So you can have your own results. Take a picture or something. I don't know. We will reset this one. So now we go to the narrow problem. And the person who wants to go next, please come. Okay, so this is the narrow problem. We go now with the take-home message. But, take this to your neck. I think it's the other one. Yeah. And yeah, I think it's on. Yeah. Okay. So these are the results for Felipe. Okay. So now we will start with the third presentation. So which one is yours? This one? Yeah, okay, great. Wait a second. Okay, yeah. Enter full screen. And this is the fourth, yes, okay. So you can start.
So good morning, everyone. My name is Felipe also. And I work with Raul Celestrino in Universidade Federal de São Carlos. I am a PhD student. We work in strontium 88 lab. So guess we work with strontium in cold atoms. So my PhD is about, in the title, the limit of mean field models. You will understand why. The refractive index of a cold atomic cloud. So in the strontium lab, we are interested in studying light matter interaction using cold atoms. So the first question I think comes to mind is how can we describe the interaction between light, any types of light, or in our case, laser light, with matter? So any material, or for example, cold atomic gas, okay? So there are different models that try to answer this. So we have two here that are remarkable ones, Lorentz and Klaus Mossotti. So the main system that we got, the simplest one, is we send a laser into many atoms here in a cold atomic gas. And we can describe, so Lorentz will describe this as a bunch of dipoles interacting with this electric field. The atoms are dipoles, as we saw in Raul's lecture, for example. He told about the Lorentz model. And these dipoles are seen as oscillators. So it's the beginning of the university, we saw and until the end, a bunch of types of oscillating systems. So it's just an oscillating system. You can calculate the frequency you will oscillate, for example, and other things. And one thing we can extract from this is, for example, the polarizability of the material. So this works for gas and works for a lot of materials too. So the main equation, I think, for this kind of model is this one that correlates the dipole, the mean dipole that light causes in the atoms to the electric field that you send. And there is a polarizability too that I put here. We already saw with our lecture last week. And with this, you can calculate the refractive index of this material, as I said, that will scale with the square root of the spatial density of your sample. But this is a problem, and we will see why. So when you think about refractive index, you can ask me, but Felipe, there are a lot of observables that you can see in your sample, that you can measure in your sample. Why did you choose refractive index? Because, as I said, it scales in these models with the square root of the density. But as you can see, I said here, the biggest natural index is 2.85 or 4 in the infrared. But these traditional mean theories don't say about this limit. So experimentally, you see that glass, water, they have the refractive index in about the order of the unity. So 1, 2, 3, 4, 5, okay. But it can scale in these models so much, and you don't have an upper bound, upper limit for this. So this orange line, I just ask you to focus on this orange line, this conventional theories, this mean field theories. Why is mean field? Because you calculate for one dipole, and then you expand to all the atoms on your sample. So all atoms will respond to light in the same way. But there is a fundamental discrepancy between these conventional theories and what you measure in these ordered materials. And this is what we will focus here. So in our lab, we not only want to study light-matter interaction, but in the dense regime. Why? Because it's in the dense regime when you see this kind of discrepancy between the theory and the experiment. So we can, the same way that Felipe already told you, we can think about the atoms when they are close enough and is comparable to the wavelength of the transition. This is what we call the dense regime, and in this regime, you see that we'll have a limitation in the refractive index, and another observable like superradiance emerges that we called collective excitations in our sample. Okay, so I say that the standard models don't apply well to this kind of situation where we have a dense regime. And we propose then the coupled dipole model. That is a new model to modulate this. So it's a big equation. Okay, I don't want to think about this. But the main thing is that with this equation, with this model, we can indeed calculate this upper limit. So here we have the real refractive index and the imaginary one. So my work is all about simulations right now, but in my PhD, we want to experimentally do this too. So in the real refractive index, as a function of the detuning of light, how much away from your resonance of the transition you are, we can see that for mean field models, for example, Loris-Loris, Klaus-Mosotti, you have this kind of behavior that can extrapolate indefinitely. But with our model, we can indeed calculate the limit that I told you that is experimentally measured, not in cold atoms because it has never been done. It's my PhD project, but for example, metamaterials, this kind of thing, okay? And the imaginary one, so here I put the relations. refractive index in its real part is related to the phase that the electric field acquires after passing through the sample, and the imaginary one related to the absorption. And in the either of the two, you can see this limitation, this fundamental limitation. So the goals for the rest of my PhD is to, beyond numerical studies that I already did, construction of the experiment. We are constructing the experiment, the cold atomic cloud of strontium-88 atoms, and implementing this experimental apparatus, and how to measure this electric field. You can ask me further, we can discuss this, how to measure this electric field after it passes the sample, and study how the refractive index could depend also in the non-linearities, depending on the intensity of the light and another types of things. So, thank you.
So you have like 8 minutes of the presentation, but as I said, it's very normal. So we have time for one question. Okay, over there.
What is asymmetrical?
Yeah, it's here.
This asymmetry happens because you have, when you're in the dilute regime, you don't have this asymmetry. You can see here that it's, okay. It's less asymmetry, you have less asymmetry, but you have a shift when you go to a denser regime. Mm-hmm. There is a well-known shift, the Lorentz shift, right? So it's just a shift that occurs in the dense regime, and there's asymmetry in the red or blue detuning. Yes, yes, you can see the maximum refractive index will depend on how dense you are. No, it's all the atoms do not move.
Okay, so let's go to the pool. So we will reset all the results for Felipe. And we go again to the first one, which is the Brodmann problem. The next one can come. Thank you. Okay, so they are your score for the Brodmann problem, which is quite nice. Then we go for the narrow problem. Okay, that's a good idea. This will be the share for the next speaker. Okay, so the one that want to come next goes to this share. Okay, so this is the results for the Brodmann problem, so very good. So for the narrow problem, and then we go to the take-home message. Okay, so thank you again. So now we will go with this other presentation. Which one is yours? ¿Dónde está? ¿Ese? Perfect. Yeah. Wait a second. Let me put it in a full screen. And you have this thing over there is to pass the slides, and the microphone is on, right? Can you take?
Okay. See? Yeah.
Yeah. Okay.
Hi, everyone. I'm unfortunately not Felipe. I'm Juan Pablo. I'm from Mexico, and this is my project, multi-component generate Fermi gas. And here, as we seen the last week with Raul, exists a beautiful zoo of moths. And here's the red one. It's made from lithium-6 atoms. Okay, and it's a photography in the last year. But we work actually with the quantum gases that produces with this start step with the classical gas, the MOT, and then I omit all the process to obtain these gases. But here here is 3 image. Where's the laser pointer? Okay. The first is the BEZ, okay, made with the molecules of 2 components of this gas. In the middle is the unitary gas, okay? It's performing the flashback resonance of these 2 components of the lithium-6. The last is the BCS case, okay, for the Cooper pairs in this atomic cloud, okay? And this is the full system that we have in Mexico, okay? And what about this degenerate system? Well, we usually use, magnetic fields. So the natural response of the atoms is the Siemens splitting. And the Siemens splitting we show here has 3 states, but we usually only use 2 of these 3 accessible states. That is the 1 and 2. I use blue and gray color, but we can say that is up or down spin. But here I use these colors because we need to add a new component. So we use the QCD platform colors to explain the systems of 3 fermions, okay? And what's my project? My project was perform these transitions from the state 2 into the state 3, and that's made from an antenna, okay? An antenna of RFs, radio frequencies, and okay, this is the results. We made a scan of the frequency until we see this dip in the atomic number, and then repeat this process, but seeing the new state populate, and we see it, the highest value of the atoms, and we measure these 2 frequencies and made characterize around a lot of magnetic fields. And here's the radio oscillations. Sorry, it's with E, no Y. Radio oscillations of these 2 species. The species in green is the species 2, and red the 3. And we see the coherence of these transitions. And yeah, this let us perform a new gas with 3 components. So it's a multi-component. Yeah, no 2 component. And that's all. Thanks.
Okay, this was less than 4 minutes, so very good. So do you have any question from the audience? Thank you.
Thank you. Okay. Yeah. Okay. We cooled 2 species and then perform the RF signal to obtain the 3.
Okay, we will go to the pool. Something that we didn't cover on the lectures that I give is that it's important also for you to learn how to make questions in a talk, like to go ahead and this is one of the best way of concentrate in a talk, to be like, okay, which question I can ask at the end. This is a very good way of be concentrated, okay? So it's important for you also to take courage and ask questions. when I do this lecture in Chile, one of the evaluations is about the question that you do during the other classmate presentations. Okay, so we will start with the broaden problem. Okay. So that's your result. You can take a picture of something. And then we go to the narrow problem. Okay, so this is a very nice result because either people did really follow you or it was not so clear, but you have a very little no and not paying attention, so this is good. So now we go to the take-home message. Okay. So then, for instance, here is the contrary. So like the people did follow you very well in the broaden and the narrow, but not so clear what you were actually doing. You see? So this can happen also. So we will go to the next presentation, which is here, please. Pedro. ¿Esta, Pedro? Yeah. Genial. So let's... Dígame.
Can I just do a comment?
Yeah.
Because I tend to disagree with the survey of the pool.
Okay.
So, because it's not, I'm not saying like it's not for you. Okay. But I tend to disagree with the broader scenario. For example, can someone tell me what is the relevance or the innovative aspect of what he did? Can one answer me?
Go ahead.
You can? I cannot. So this is what I'm saying. I think the broadened scenario was not really
I mean about the multi-species gas. This is what I get.
Yeah, but why? Why to do it? You see, I think on the broadened scenario, it's important to say where your work is on the state of the art, why you want to do a multi-component Fermi gas. There are many, many reasons, but you didn't say here. So if people that are not working with Fermi gases, they don't know. And people said, okay, yes, for the broaden, but no one knows why he wants to do a multi-component Fermi gas. I don't know.
That's what I said at the beginning. We need to answer very honestly the pool. Otherwise, it's not good for your mate. This is okay.
Exactly. So it was not clear. Why is it interesting? It's very interesting. I'm sure you know it. But if you are talking to a broader audience, especially here, that just a few of people work with Fermi gases, you have to motivate to say, okay, we want with Fermi gases, and we usually people use two hyperfine states in these systems. We want to use 3 because, this is your broadened picture. You see?
This is very important. No, it's okay. I mean, So what Patricia is doing is what someone, for example, in your commission will do. When you have your thesis presentation in private and stuff like that, they will tell you, okay, you did wrong here, and you need to improve that, and you really need to be like willing to accept the criticism and make it better the next time. This is why you are practicing here, and this is why in this school we put this soft skill training, because you don't know how to present and to communicate. And this is okay because you are learning, but you need to learn. And by learning is practicing. So it's okay, okay? Yeah, let's go to the third, no, I don't know the name, the number for the next presentation, and then the next one can come to this share. Okay, go.
Hear me?
Yeah.
It's okay. Okay. Good morning. My name is Pedro Rosario. I am PhD student in Sao Carlos. This is a work that we are almost finishing to send to archive, so it's new results that you are going to see. So yeah, and basically the idea is to talk about multi-level system, multi-level entanglement, but why entanglement? Why entanglement is important? Well, the idea is very simple. Entanglement is like money. We can use money for different applications, and so entanglement also can be used for different applications like quantum metrology, quantum sensing, quantum teleportation, etc. For two particles, we already know how to quantify entanglement. We can use concurrence, negativity, etc. But for many particles, we already don't know how to quantify entanglement. It's a problem. It's still an open problem how to quantify entanglement. Only for pure state, we know how to quantify entanglement. But the problem that I want to solve, the problem that I'm interested in is in quantum tomography or in experiments, because people normally when people want to study entanglement in experiments, what they need to do is to do quantum tomography or the density matrix. And this is a difficult problem because when you increase the number of particles, the complexity of quantum tomography increases exponentially. So it's a problem that we need to solve. And the idea to solve the problem is to use entanglement witnesses. And the idea is very simple. Imagine that you have a machine, and you put in this machine a quantum state, and you can ask to this machine, is this quantum state entangled or not? And the answer can be yes or I don't know. The advantage of use these entanglement witnesses is that we don't need to do quantum tomography. We only need to apply collective measurements or to measure collective operators, like for instance, collective spin or temperature or entropy, etc. So what we are doing is that we are measuring the collective electric field. We want to measure the collective. We have many atoms, they are emitting light, and we measure the electric field. Only measuring the electric field, we can say if the quantum state of the system is entangled or not. That's the idea. So some results. As I told you, what we are doing, we have a system of many particles and atoms, and each of these particles is a multi-level system, arbitrary number of levels, and we are measuring the electric field of the system, and only measuring the electric field of the system, we can say if the system is entangled or not. So we can do the calculations very easy, and we can show that if this inequality is not satisfied, then the system is entangled. Otherwise, we don't know if the system is entangled or not. These are entanglement witnesses. So we are applying this to different states, for instance, decay states, singlet states. What we are doing here is the following. We have the atoms, that I am showing here, and we are moving the detector in different positions, where the detector to detect the light of the atoms. We are creating this spherical surface. So the red regions correspond to cases where we are detecting entanglement, and the blue, the region where we are not detecting entanglement. As you can see, we can always detect entanglement in many directions of the detector, and there are other directions we are not detecting entanglement. But the important point is that we can do that for many particles. For instance, here we are considering 10 to the 3 particles. So that is very difficult with quantum tomography. That's it.
Great. We have 3 minutes and 36 seconds. So great. Do we have any question? Any question from the audience? Go, Felipe. Repeat the question because.
Yeah, so we can witness different correlations beyond quantum entanglement, like discord, non-locality, steering, etc. I haven't seen anyone doing that, but I suppose it's possible. It depends on the quantum state that you are studying. But yeah, in principle, it's possible. But the most important is quantum entanglement, so this is why we are studying quantum entanglement in general. Yeah.
Okay, so we go to the pool and try to answer as honest as you can. Be honest, yes, this is important for everyone. Okay, So there you have the Brodden problem. And the next speaker can come. Okay, just take the thing. Okay, so this is the result for the Brodden problem. Now, thank you. And then we go to the narrow problem. Okay. And now we go to the take-home message. Okay, so these are the results. So we go now with the next presentation, which is Rodriguez. ¿Esta? Rodriguez de Paz? Yeah. Okay, so wait a second that I put it in the full screen. Okay, you can go. And the microphone, can you see if it's working? No, okay.
Right, test, okay.
Okay.
Okay, how we start?
Yeah.
Good morning, everyone. I am in my project. I try to study analytically dipolar supersolids in bubble traps, which are systems like this. How can I point?
The pointer has to be. This button.
Okay, thank you so much. Which are systems like this. Okay, I have identified two broad problems. The first one is kind of to explore as most as possible the competition between geometry and different interactions to try to find new physical phenomena. And one of these new phenomena is the new novel phase of supersolids. And the other broad problem, it's try to advance the theory of supersolids. And supersolids are in kind of a paradoxical phase because they present at the same time solid and superfluid characteristics. Okay, okay, just a second. And we are working with this because the main tryings to advance this kind of theory, it demands numerical methods, and we are trying to find new analytical ways to do it. And another motivation to me is because there are few people in LATAM studying it. Okay, these are some representations of supersolids. One can see the crystal structure and the background superfluid. Okay, the intersection between these two broadened problems, it's my narrow problem, and I am interested in study this phase in this kind of system. I am showing some quartz of these profiles of supersolids in the bubble trap, but especially I am trying to reproduce the numerical phase diagram of this kind of system. When group has pointed the regions of the domains of Bose-Einstein condensates and modulated phases, in particular in a narrow region, the supersolid phase. And I am trying to rebuild this phase diagram using analytical methods. And the the main message I would like to pass is, yes, we can to produce a phase diagram kind of similar to the numerical one, but we must improve it. And we are employing some efforts to do it. In particular, we are trying to infer how the dimensions, how the size of the crystalline core changes across the phase diagram. So when we can reproduce this phase diagram as better as we can, we expect to be able to change a little bit our geometry to test and other configurations, and finally we expect to calculate some properties of supersolids and try to, and with this we will try to contribute a little bit for the broadened problems. Okay, thank you so much, and thank you for your patience.
So this was 4 minutes and 20 seconds almost. So do you have any question from the audience? We need a question, so ask a question. Thank you again.
Thank you for the talk. What's the difference that your project bring to the last analytics results that the community had, and what you added to the results?
Just confirming, you are asking to me what is kind of the advantage to work analytically. No?
What's the difference from your method to what you did to analyze analytically this problem? Because if it was like easy and straightforward, it would be done before. What you're trying to do?
You say numerically what the others can did. Okay. Well, I didn't have time to mention it, but they have solved the extended Gross-Pitágoras equation, and it's so difficult, and it spends so much time to do it, and I am trying to do it through an ansatz to capture the azimuthal profile, and well, it's what I try to do. I catch the equation, and using second quantization formalism, I obtain expressions, and I am varying the ansatz to try to reconstruct these diagrams. Have I?
Approximation or nothing like that?
No.
Okay, you can keep discussing later. Thank you for the question again. So now we will go to the pool, and then the next speaker can prepare, please. So another thing that I wanted to say, normally when I give this lecture, since it's in Spanish, we first try to cover the communication thing in your own language, because of course adding the English part is another extra issue for all of you, and this is okay. So this has a double difficulty, so to say. Okay. So we go to the broadened problem. Just go ahead. So there you have. I think that one good strategy that you try to do is that you were this is my broadened problem, this is my narrow problem, this is what I want you to take home. This is a good strategy also to try to make your presentation a bit more clear. So okay, so we go to the other one, and the narrow problem. Okay. And then this is your, and then we go to the take-home message. Okay, so these are the results. So now we will move to the next presentation, which is this one? Yeah. Okay, great. So, yeah, let's see if it's, no, you have to turn it on.
Now it is working?
Yeah. Okay, so you can start.
Yeah. Hi, everyone. I'm João Victor. I'm a PhD student at the Universidade Federal do ABC, and I'm interested basically in full-wave mixing. So, the pointer. Yeah. So, we already heard quite a lot about full-wave mixing from the lectures from Irina last week. So, it is this nonlinear third-order process where a pump beam interacts with the media, and as a consequence of the interaction, a pair of beams known as probe and conjugate are produced. So the interesting thing about this nonlinear phenomena is that it is, well, two interesting things. First is that it is a well-known source of two-mode squeezing. So if you look at the individual beams, they are quite noisy. But when you look at the intensity difference between these beams, they have noise compression, right? Which we have known for a very long time. And another thing that has also been explored by the same group which published this first work with atoms. So one thing, I'm working with atoms, so atomic vapors, right? So another interesting thing is that they present entanglement between their sideband bases. So I'm not sure if anyone is familiar here with, if everyone here is familiar with sideband approach. So pretty much you have a carrier frequency for probe and conjugate, and you can look at the, for instance, lower and upper sidebands of this structure, right? And this work used this entanglement between the sidebands to create entangled images. So the main question in literature is, how are these correlations actually distributed among the sideband modes, right? So this is like the main problem. Well, you can, experimentally, you can approach this in two ways. The first is to perform your direct photocurrent measurements, so like homodyne measurements or direct intensity measurements, where unfortunately you have no access to the individual contributions of the lower and upper sidebands, so they're like symmetrically combined in this fashion. Or you can perform a measurement using, for instance, a resonator, like an optical parametric oscillator, where you can individually access all the bipartitions of this four-mode scheme. So like in this fashion, all these different bipartitions. And in fact, a recent work done here in Brazil from a research group in USP showed that four-wave mixing actually, with atoms actually produce a asymmetric entanglement structure, in the sense that there are situations when you observe entanglement between these bipartitions individually, but you cannot see entanglement if you look at the direct photocurrent measurements, in this sense that it is hidden. It is hidden in the bipartitions of sidebands. So the question that we made ourselves is, does this also hold for other kinds of quantum correlations? So we already heard a great deal about quantum correlations, different forms of it, from Professor Stephen this week. And we have learned that EPR steering is this intermediate quantum correlation between entanglement and Bell non-locality. And the main fact here is that it is inherently asymmetrical, meaning that you can have situations where one system A can steer system B, but the converse is not true. B cannot steer A. So that makes steering like a perfect candidate to study this question, like does this asymmetrical feature also reverberates to other forms of correlation? So this is the main question that we wanted to answer. And to work this problem, we use a very nice microscopic model due to Quentin Glorieux. in 2010. And the nice thing about this microscopic model is that it captures all the different experimental parameters of our system. So you know exactly what pump power you should use, what detuners you should use, how you should set up your experiment to observe these correlations, for instance. So it has this double lambda structure with this interaction Hamiltonian that I may explain later, like in the poster section of question section. And we use the development from this microscopic model to calculate steering using this steering criterion by RAID, where you calculate like the product of the variances of quadratures, right? So what are our main results? Here I have two graphs where I plot as a function of the frequency analysis, like the analysis of our sideband. And we look at two different partitions, 1 and 4, so like lower sideband for the probe and upper sideband for the conjugate, and the other way around for the lower graph. So in the former case, we see that we have a region, this region, shaded in red, where you can have one-way steering. So like B can steer A, but A cannot steer B. So we do see this asymmetrical structure. And the other interesting thing is that this bipartition presents a much larger bandwidth than the other partitions. So this is like from 7 to 10 megahertz, and this is from like 5 to 6 megahertz. So you have a symmetry not only by the presence of one-way steering, but also to observe that one pair of these bipartitions is more correlated than the other. So, just to conclude, I believe I already passed my time. We see that indeed the twin beams produced by four-wave mixing are strongly correlated in the sense that not only they produce entanglement, but they also produce this stronger type of correlation known as steering. And also, it's that steering presents a symmetrical correlation structure on the sideband basis, meaning that you have one-way steering scenarios when you look at individual partitions. And this opens pretty much like new potential applications for four-wave mixing with atoms. So like Stephen mentioned, you can use, for instance, this steering for implement different quantum communication protocols, such as quantum key distribution. So that's a good place to stop. Thank you, everyone, for the attention.
So you had 6 minutes and 50 seconds. It's okay. So do we have any question? Aha, many. Good. This is good because people understood you. You have many questions.
Hi. Thank you very much for your talk. I'm not quite sure what you mean by asymmetric correlation. If you can explain a little bit more, what is this asymmetrical correlation structure?
Yeah, so it actually has two senses, two meanings actually in this presentation. When I say asymmetric, it's not only that you have, in the case of entanglement, asymmetric means that you can have like more correlations in one individual bipartition. So like this partition 1 and 4, so when you take the lower sideband from the probe and the upper sideband for the conjugate, you observe stronger correlations comparing with the other partitions. So this is the meaning of asymmetric. The sidebands are not homogeneously distributed, right? And the other meaning when you talk about steering is that you have this so-called one-way steering, which is asymmetrical, meaning that one system, one part can steer the other, but not the other way around, right?
Okay, so we go to the pool. Here. Reset. Okay. Reset. Okay. Reset. Okay, so let's go. Okay, for the people that is coming now, we have 4 people to go. So it's you 3 and you. So try to pay a bit more attention on the timing because otherwise we will not be able to. We have 15 more minutes before lunch. So try to keep it on time if possible. Okay, so we stop here. So this is the result. Then we go to the narrow problem. Okay. And then we go to the take-home message. So this like exercise about trying to see what is the broaden problem, narrow problem, take-home message, you can do it in every seminar also. This is a very good way of training yourself. Okay. So we go to the next presentation. Where is it here? Is this one? This one? Okay. Okay, but this is too many slides. It's too many slides. Yeah. Okay, you see it, but you need to be on time, please.
Oui, oui.
Okay. View. Okay. So you can start.
Hi everyone, I'm undergraduate student. I'm Inês Barros and my professor Bertolio de Lima Bernardo. I'm from University Federal of Paraíba. And okay, we work on a study in polarization and environment effect on wave particle duality of light. And the first we consider an inequality called EGY inequality. And everyone can hear me? Okay. And we study distinguibility and visibility. Distinguibility in the experiment of two paths. So we study distinguibility between the two possibility paths of the experiment, and visibility in an interference fringe produced in the experiment. So when we have the maximum value of distinguibility, we, meaning 1, we have corpuscular behavior. So we don't see visibility. And when we have a maximum value of visibility, we don't see distinguibility. And we see wave behavior. In this work, we want to see the environment acting in the system and see what happens to the distinguibility and visibility. So we consider the experiment, and the path 1 and path 2 is taken by this CADS vector, and the polarization horizontal or vertical, we consider these vectors, these CADS. So consider the density matrices. We can take the visibility and distinguibility in terms of these terms of density matrices. And we take some examples. These examples we take in pure states, so we don't consider yet interferences in the systems. So we can see the maximum value of the relation in visibility and distinguibility is 1. And we take this wave function and assume some values of A and B. In this case, we take first B equal to 1, and when we have A equal to 0 and A equal to 1, we can see the maximum value of distinguibility, and we don't see visibility. Okay, here. And in this case, when we have A equal to root of 1/2, we can see the maximum value of visibility and no distinguibility. So we know where is the path taken by the photon, and here we know the path taken by the photo. So we see a maximum interference, but we don't know where is the path taken by the photo. The second case, we consider B equal to 0. So we have a maximum distinguishability and no visibility. In the third case, we consider B equal to root 1 of 1/2. So we have here two kinds of polarization. So is impossible to have a maximum value of visibility, but the relation continues the maximum value, like 1. But when you go to open quantum systems, we see that the maximum value of this relation is not, we cannot see the maximum value. So we use a Krauss operator because he brings in him the relation in the environment and the system. In first case, we see the relation is starting 1, but not continuing 1, has a decay. And in the second case, the same happens. It starts 1, but has a decay. And one curiosity is the distinguishability has a difference down and up that is not very common to see in non-Markovian systems. So we are trying to analyze this thing. And is this some conclusion, observations, and conclusions?
Okay. So it was 5 minutes 30, but she's the only undergrad student of the school, and she is here. So pay that into attention. So do we have any question from the audience? Please. Patricia.
So I think a general also, when you are doing a short presentation, like 3 minutes one, you have to think about the number of slides you're going to show. There is a kind of rule of how much time you spend on a slide. It's something between 30 seconds and 1 minute. So if you are doing a 17 slides, you are not going to do it in 3 minutes. It's impossible. So you take like 30 seconds, half a minute per slide. This is a good, I think, it's a good compromise for it. So 3 minutes, you can say 6, 7 slides maximum, because otherwise also people cannot follow. It's too much thing. So it's general.
Just to clarify that she talked to me first. It's just that she's going to present this next week, and she didn't have the time to adapt it to. I knew that she will go fast in order to make it in the time.
Yes, it's.
But it's a good advice for everyone. You need to keep in mind this timing for a slide. It's just not her case.
I understand, but like for the future,
for the
when you do 3 minutes, think about how fast can you talk one slide. It's really, you cannot go much faster than 30 seconds just to introduce the slide.
So we will go to the tool, and then I think that we will have time for just one more. And we have 4 people here, so try to decide with Kachipun or something, but because I don't think that we will have more time. Talk to each other, I don't know. For now, we will do the tool, the pool for dígame. ¿En 2 minutos? Sí, o sea, si pueden hacerlo en 2 minutos, ideal. Team pool, okay. Okay, so they want to go without pool, without questions, but have the opportunity to be here, okay, and try to make it on time. Okay, so this is the pool for her. Then the narrow problem. We start after the time? Okay, I thought that was we have started at the beginning. Okay. So this is the narrow message, and then this is the take-home message. Okay, so we will do these 4 last presentations without the pool. Okay. So, ponte la cosita, Fabi. La cuestión esa para que la cámara te persiga. Sí, sí, sí. ¿Y la tuya dónde está, Fabián? La mandaste, ¿verdad? Sí. Guión bajo FR. No lo veo, no lo veo. Aquí, está. Ok. Ya. So, go. It has to be like a green button there on.
Now, yes?
Yes. So
Nice.
do not turn off the microphone. Okay. Go, Fabian.
Okay, so the ability to generate and manipulate quantum states of light is a key task in quantum information science. In particular, by controlling their spatial degree of freedom, we can design new secure quantum protocols of high information capacity in higher dimensional Hilbert spaces. I know. Okay, so in four-way mixing, the twin beams generated are spatially correlated. But we saw that there wasn't a general framework to describe any order of interaction for any spatial distribution, okay? So we model that process and we get the statistical properties of both beams, which includes the cross-correlation. Okay, the model works for the plane wave cases, but we wanted to try multiple beams configurations. In this example, I show you a double Gaussian beam seed intersecting at the center of the cell, and we can control the phase. You have a plus-plus Gaussian and a plus-minus Gaussian. And we see that the intensity pattern looks almost the same in the sense that you see 2 Gaussians in both beam, probe and conjugate, but the cross-correlation has a difference. You see a negativity in the cross-correlation, and this means that you cannot retrieve the information from density pattern, but you have to measure the spatial correlation. And we can recover the initial, or we can propagate information that can be measured just in the cross-correlation of both beams. Muito obrigado pela atenção.
Okay, exactly 2 minutes. Good, Fabian. Okay, so then you can discuss with Fabian later. He's presenting his posters today, so you can go and then go with further questions. So the next one, please, with the power nickel. So your presentation is. ¿Cuál es la tuya?
Hola, hola.
¿Cuál es la tuya?
Vlatko, la última.
¿La última?
Sí.
Perfecto. Gracias. Okay, and go.
Hi. Okay. So I'm Carolina, and I'm presenting a work from my colleagues, not me, but it's in our, from my group, the Laboratory of Ions in Buenos Aires, Argentina. So here is our ion trap. As you heard in this school, ion traps are useful for quantum sensing, quantum simulations, and also fundamental physics. As is this case, we want to study heat transport in 1D systems. This has not been measured and is different physics because of the dimension. So the problem is that for this, you need to have information of the velocity and temperature of each ion locally, and most methods gives you information about the collective modes. So what we need is to do local thermometry. A standard known method that we saw with Irina is the dark resonance spectroscopy. So if you have a 3-level systems, and depending on the tuning of the lasers, you can hit a dark resonance. Then you can see here that depends on the temperature, meaning also the velocity of the ion. So the problem is actually most people work with, like us, more level systems. This is our calcium 8-level system. And here we have 4 dark resonance for each combination of lasers. And the thing is, solving this exactly to get the temperature takes 1 day. It's just one simulation with one set of parameters. So if you start making approximations, you can lead to inaccurate results here when you can see the different temperature profiles. So what they did is to run simulations with different models and approximations to compare them. And what they found out is that this approximation, it's in principle is wrong, but what they find out is you can calibrate it and recover the exact solution. And this takes the time from 1 day to 2 minutes simulation. So I don't know the time, but the conclusion is that with this new method, we can estimate local temperature of each ion, not only accurate, but efficiently. We can explore the experimental parameters to implement this, and we can get what I found interesting, get an insight about the heating and cooling dynamics of the ions. So thank you.
Okay, thank you.
How was the time?
2 minutes and 45 seconds. Okay. So the next one, ¿cómo se llama tu presentación? What's the name of your presentation?
VDP.2 Hanson.
Arriba no lo veo. Hanson. Pero el punto 2.
Sí, ese.
¿Ese? Ya.
Sí.
A ver, vamos a ver. Okay.
So, I'm Rafael. As a Kickstarter, I'm not from here. I'm not from the quantum field. I'm from nonlinear physics. So I study this kind of patterns and solitons. So what is the main problem? Well, we found this kind of transition in a fluid system, which is parametrically pumped to localized regions in space where kind of punching the fluid from underneath. So we have this transition in the rotating wave approximation or the envelope of the fast oscillations. We have stationary states and Rabi oscillations or Rabi-like oscillations. They have a P or 2 phase difference among each other. So the main problem is we didn't know what to do this in a fluid system, so we wanted to explore the robustness of this as a mechanism or the mechanisms behind this to see if it works in another kind of system. So we wanted to see if we apply the same mechanisms into a quantum system, a simpler system. We have 2 harmonic oscillators coupled. We have a parametric drive. We have nonlinearities accounted for Kerr effect. So if we have losses also, we can see the same kind of behavior. So we did that, and the first approach, as I come from a mean field, come from macroscopical phenomena, we did mean field approximation. We found the equations of motion for the current states, and we found kind of the same regions for this parameter space, so we can change the states we are if we exert more strength of the pump, or we change the detuning relative to the natural frequency. So we have all of these states, and we wanted to see now what does the quantum noise to this kind of stuff. So we went a bit further, and we did the Trucade-Wigner approach. So we had Langevin equations. We have kind of a Wigner function with entirely positive. And so we did simulations, and we observed that there's phase diffusion, module diffusion. Also, we can suppress kind of strange oscillations are going here. And we kind of observed the main result, I will say, is that the quantum noise or the randomness does not destroy the oscillations after the validity of or we lost the validity of the truncated Wigner approach. I mean, we have way low occupations here, so we don't know if it's a quantum effect. And it's not a quantum effect, but we wanted to see now treat the system the quantum system in Limblad equation or some kind of approximation. So The main idea is that we still have a kind of correspondence. It's not a quantized fluid, but it's a correspondence in the mechanisms of drive and dissipation in this kind of system. So that's it.
Okay. 3 minutes and 9 seconds, Wes. Tu presentación, your presentation, what is the first one?
No.
Okay, which one? This one. Okay. Okay, this is the last one, and then I will just give 30 seconds comments, and then we go to lunch. Okay, go ahead.
Can you hear me? Yes. So good morning, everyone. My name is Thales. I'm working with Felipe and Professor Raul, who is my supervisor. I'm a master's student in São Carlos. So in our lab, we study light matter interaction. We use a cold cloud, a dense and cold cloud of strontium-88. And then we produce these clouds in USMOT and infrared ODT. But the most important here is that our cloud is dense. When we increase the density of the cloud, some collective effects emerge, and then we see multiple scattering in this cloud. So the main problem here is that we can describe the interaction inside this cloud. We cannot describe the light transport because of these collective effects. So take a look in your data of the transmission coefficient. We see that the multiple scattering makes a background for the coherent transmission. So if you want to measure some physical quantities like the optical depth, the refraction index, and study modifications in some models like the Beer-Lambert law, the coupled dipole model, we can't because of this background in the transmission coefficient. So we need to distinguish the coherent transmission and the incoherent transmission. So how can I do that? Is making a heterodyne detection is not homodyne because the local oscillator and the signal beam has not the same frequency. But if we look at the photocurrent that reaches a balanced photodetector, this photocurrent carries the amplitude of the two signals, the local oscillator that is a strong field, and the signal that passes through the sample. These signals carries the relative phase between these two beams, and the amplitude. So with this heterodyne detection, we can measure both the quadratures of the electric field transmitted by the cloud. And then I will draw very quickly. If we measure the electric field, we see that the scattering light has, in a given direction, a random phase. So if we measure the phase of the electric field and make an average, we can eliminate the incoherent transmission. So there are three remarkable results that I want to show you. That is the phase measurement. We measure the phase with satisfactory precision. So it's obtaining the phase that we can eliminate the incoherent part of the electric field. The second result is a calibration stage with which we use a set of density filters to calibrate the system. And I think it's the most important result of this work until now. And we measure powers of femtowatts, which is powerful. So the amplitude, measure the amplitude is which allows us to measure these physical quantities that we want. And the last, we measure the transmission through a liquid sample. This is a good result, but the decay factor of the Beer-Lambert law is wrong because we had a problem and we need to solve that the mixer used to demodulate the electronic system signal is non-linear, but we need to improve this to implement in the main experiment. So we want to do this implementation in the next year. So that's it. Thank you.
Great. So it was 4 minutes and 26 seconds, okay? So the idea of this lecture, of this course that we offer this year, these soft skills trainings for you to learn how to present, how to communicate, and you also have the feeling of how hard it is sometimes to be here, and you have the difficulty, the extra difficulty that will not be in your native language also. So at the end of the day, the main message is you have to practice and try to do the same tonight, for example, with this afternoon with the poster. Try to see, do you understand the broad problem, the narrow problem, what the person is actually doing and why this is important to solve whatever in the respective field, and try to do also that in your seminars, back in your school, in your university. You will see that some professors, they do not either know how to present, and they fail about knowing the audience and try to communicate the broadened picture for people not to get lost and to be able to follow what you are trying to communicate at the end. So I really hope that you have enjoyed this soft skills training in this school. Thank you.